direction of v2 sub x is that. It's positive, and that all makes sense. Okay? All right. Now we need to know v2 sub y. So v2 sub y is going to equal right there. So it's my u1 sub y times sine squared theta. So got that in. v2 sub y equals 1 meter per second times sine 60 degrees squared. v2 sub y equals 0.75 meters per second. So then we have, I'm going to squeeze this at the bottom here. So as before, we have v1 sub x equals negative, right here, negative v2 sub x. So it equals negative v2 sub x, which is to say equals negative right there, 0.433 meters per second. I'm running out of space, but I guess I'm going to screw that anyway. So then I have v1 sub y. Can you guys see this, or should am I wasting my time? I'm trying to avoid erasing those for the moment. So v1 sub y equals u1 sub y minus v2 sub y, which is to say it equals 1 meters per second, minus the 0.75 meters per second, so it equals 0.25. So this distance right here, this guy, this is v1 sub y, equals 0.25 meters per second, et cetera, et cetera. Okay? And so those are our answers. We have v1 and v2 in terms of their x and y components. All right? And so now I want to be able to check that these satisfy the general equations I gave you before. Now I am going to have to erase this stuff over here. So I want to make sure that these answers, because we had the equations before were conservation of momentum in the x, conservation of momentum in the y, conservation of kinetic energy because it's an elastic collision, and then the fact that any change we make in the velocities happens along the line of action. Those are the four equations we had that constrain this in a more general sense, where you can have different diameters, different masses, multiple things moving. This answer should still satisfy those equations. So we want to check that. Okay. So, first of all, we have conservation of momentum in the x. All right? Now, because they have, so what is momentum? It's mass times velocity. Because these have the same masses drop out, right? Each time I do a mass of the one times its velocity plus mass of the other times its velocity. All masses are the same, so masses drop. Everybody comfortable with that? Yeah, maybe?
Yeah.
Okay. Thank you, Joe. I appreciate that affirmative answer. I really do. Now, I mean, I haven't said it too. Didn't put anything else. All right. So what I want here is u1 sub x plus u2 sub x. So that's momentum in the x beforehand, with the masses dropped out. Should equal v1 sub x plus v2 sub x. So this is pretty trivial. Most of you should remember this from lab. So what is u1 sub x?
0.
It is 0. And what is u2 sub x?
0.
Also 0. We're not going anywhere in the x. And what is v1 sub x? We found it to be right there. It's negative 0.433 meters per second. And what is v2 sub x? No, v2 sub x is clear. This is negative. v1 sub x 0, and so we're fine. So momentum in the x is conserved. Next up, we want to have momentum in the y conserved. So this is mom sub x. So now we want to do this in the y. So we have u1 sub y. Again, the masses are going to drop out for the same reason as before. Plus u2 sub y equals v1 sub y plus v2 sub y. So we put in our values, and what do we have for this? What's u1 sub y? 1 meter per second. 1 meter per second. Plus, what's u2 sub y?
0.
0 equals, what's v1 sub y? v1 sub y is indeed 0.25 meters per second. And this is 0.75 meters per second. We can all do that math and figure out, yes, that does work. 0 this one? That was u2 sub y. The object ball was stationary, so it's has 0 for both components. u2 sub x and u2 sub y are both 0. To solve this out, okay, so there, that works as well. So this is mom sub y. All right, so next up we have conservation of kinetic energy. So for conservation of kinetic energy, again, the masses are going to drop. So I can write the conservation of kinetic energy. I need to have squared, one half mv squared, right? Is kinetic energy. So I need to have that beforehand and after. With the m's all dropped, because there would be an m in every single term, and the m's are all the same, so I can drop them out. To find the magnitude of the velocity, Pythagorean theorem. So we have, over here we have u1 sub x squared plus u1 sub y squared. And if I were to add those, take the square root, that would be the magnitude of the velocity, right? Except I want the velocity squared, so I don't have to take the square root. So I'm good, right there. So I have that. I would be taking half of this, except I'm taking half of the other ones, so I'm going to divide the whole thing by 2. So now I have the second ball. So I have u2 sub x squared plus u2 sub y squared. All of this over 2. So with the masses dropped out, this is my kinetic energy beforehand. So I'm going to start writing pretty small here, I guess. And so this is going to be, now it's v1 sub x squared plus v1 sub y squared plus v 2 sub x squared plus v2 sub y squared also over 2. So this needs to be true. The kinetic energy is conserved. This is our kinetic energy equation where the masses drop. Okay, everybody gets this? All right. So what do we have? What is u1 sub x? It is 0. So I have 0 squared plus I have u1 sub y, which would be what? 1 meter per second squared. And then I have u2 sub x and u2 sub y are both 0. So 0 squared plus 0 squared. And over here, I have v1 sub x, which was what? Yeah, so it's negative 0.433 meters per second squared plus v1 sub y, which was 0.25 meters per second squared plus v2 sub x, which is anyone? 0.433 meters per second squared plus v2 sub y, which is 0.75 meters per second squared. Both of these divided by 2, obviously this kind of cancel out as well, but we'll just leave it in there for the moment. So divided by 2 2, this one divided by 2. And so what do we get here? We have 1 meter per second squared divided by 2. Okay. Here's our units dropped out. We have 0.5 meters squared per second squared. That's what we've got. And so if we had our unit, our mass still in here, our kilograms, we have this is, and we have kilograms still in here, this would be the unit of measure, this would be the joule. So it all makes sense. And so then on the other side, I'm going to save you the trouble, but if you feel like it, you can run this through with your calculator, and you will find this also equals 0.5 meters squared. So what? Okay. So this shows us that our kinetic energy is conserved. So all of this is kinetic energy. And on the homework, when I say KE, I mean kinetic energy. The homework's posted to Moodle. So then lastly, we need to have, I said the general equation was the tangent of theta equals, and I derived this last time, v2 sub y minus u2 sub y over v2 sub x minus u2 sub x. Okay? So now I have, we found theta is 60 degrees. So I have tangent of 60 degrees needs to equal the v2 sub y, which is 0.75 meters per second, minus u2 sub y, which is 0, because u2 is moving, over the v2 sub x, which is 0.433 meters per second, minus u2 sub x, which is, again, 0. u2, once again. So if you do this out, you'll find that the tangent of 60, this guy right here, equals 1.732. And if you do 0.75 divided by 0.433, you will find that also